Bienvenidos, yo voy a ser la intérprete para la sesión de hoy. Si ven en su pantalla van a ver un globo en la parte baja derecha. Ustedes tienen que hacer clic ahí y escoger el idioma que desean escuchar. Si es que desean escuchar la interpretación simultánea porque la charla va a ser en inglés. Eso, que lo pasen bien.
Go.
No, thank you, Gloria. To all our attendees, we remind you that this talk will be in English, so those who want to hear the translated version in Spanish should look in the tools menu below for the translation option in Spanish, where our translator, Gloria, will be interpreting this talk. So with that being said, we welcome all of our attendees to the last talk of the online version of the International Seminar for Engineering Leaders, or ISEL, of the 2020 edition. My name is Bernardita Undurraga, and I am one of the general coordinators of the Engineers Student Council, CAI. The sixth and the last SDG that we will discuss in this seminar will be SDG 13, Climate Action. For this talk by experts, we meet Tancredi Botto, who is a physicist and inventor. He was a research scientist at the MIT Nuclear Sciences Laboratory, founder of New Ambition, created and patented with a group of Chileans. This is a technology that allows the mining industry with X-ray vision to boost the recovery of metals, increase safety, and better manage waste ponds. Tancredi will give us a 30-minute presentation on the topic high-impact industrial applications of particle physics. During the presentation, we will close the Zoom chat, but we will open it at the end of the presentation, where we will start the round of questions that will last around 20 minutes. You can ask your questions in English or in Spanish in the Zoom chat. It is important to emphasize that we are also broadcasting our seminar on our YouTube account, CAI TV. Without further ado, we welcome Tancredi Botto.
Thank you very much, Bernardita, and good afternoon to all. Thank you for the invitation. It's a pleasure. So I will spend the next 30 minutes of your time describing a little bit my career trajectory and how this is now all connected to Chile and to sustainability goals. So a little bit about myself. I speak in English, but I'm Italian. I was born in Genoa, Italy. I studied in Italy, as a matter of fact, physics, and got a PhD in Holland at the National Institute of Nuclear Physics. After that, I moved to the United States. I was hired as a scientist at MIT. And while at MIT, I was doing basic science. I was a scientist. And the questions we were asking at the time is, for instance, what is the shape of a proton? It sounds a very academic question, but there could be very deep reasons why a proton is not perfectly spherical. And by the way, it isn't. We did measure this at MIT Bates. We also work on the charge distribution of a neutron. A neutron, as you know, is the neutral sister of the proton. However, when you look at it at a very small wavelength, a neutron actually looks like a negative core, a positive core with a negative cloud. So why is that? That was all applied science and as a basic science, and of course was very interesting and rewarding to me. But at some point, there was a change in my career. In 2005, I joined Schlumberger. Schlumberger is, at that time, was a giant multinational company involved in all aspects of exploration on the ground, primarily for oil and gas. It's not because I had a particular affinity towards oil and gas. I actually did not know that physics had such a deep important role in underground exploration. So I like to say that I got my second PhD during that tenure. And I work on a number of very exciting and very technological rich projects. Here's some pictures. The primary goal of my research, the group I was working with, was replacing nuclear sources, which are commonly used in oil and gas, by something that you can turn on and off. So to generate nuclear radiation, you can use particle accelerators, but to bring it to a hole underground, it has to be a very small particle accelerator. So one of the first projects I worked on was the Betatron X-ray source. You can see here a picture on the top right. A very old technology, but we transformed it to something very small. I'm very proud of having proposed and patented and conceived and developed a completely new type of particle accelerator, what is conventionally called a linear accelerator. You can see this here in the middle picture. We replaced existing technology coming from the Star Wars years that never was commercialized with something that was potentially much smaller in the size of a cigarette. I also work on many other topics, not just in nuclear physics, in microwave, electromagnetic measurements, NMR. And I also enjoyed very much collaborating with many universities. I live in Cambridge, Massachusetts, so right in between Harvard and MIT. That's also where my lab was. So I had numerous collaborations with both Harvard and MIT scientists, growing students, postdocs, and overall doing good science. Okay. One of the projects I worked on while in Schlumberger was this idea of using cosmic ray particles, and we'll get to that, in order to do measurements underground. We refer to this as the CRY project. It's a bit of a joke. CRY stands for Cosmic Ray Imager. So the message I want to give is what I want to spend the next few minutes about is the concept of muon radiography. You're all familiar with an X-ray radiography. That's what you get at the doctor's office. But you can also do the same instead of using X-ray, using muons, which are particular subatomic particles. So we're gonna explore what does it mean, what cosmic ray means, nothing to worry about, and the concept of muon radiography and the technology that you need to develop in order to utilize it, and some possible applications. All right, so let's start from the beginning. Let's start from space. You may not realize, but outside of our atmosphere, we are constantly bombarded by so-called primary cosmic rays. These are particles, nuclear particles, such as protons or light nuclei, like helium, but also heavy nuclei like carbon and iron, as you can see in this picture, which are constantly reaching Earth from everywhere in space. We know where they come from. These particles actually do come from supernova explosions. We don't actually understand how they can be so energetic. So the Earth is swimming in this bath of subatomic particles. The source is switched on at every time. These particles arrive at the top of our atmosphere, and now they finally exit interstellar space. They find air in low density and increasing density, and they start generating a cascade of subatomic products that they quickly decays. But one particle, that particle is called the muon. For relativistic reasons, the muon lifetime is long enough that it can reach the surface of the Earth and penetrate deep underground. The Earth's shell, atmospheric shell, is considered to be about 30 kilometers deep. And it doesn't take much to traverse it at relativistic speeds. The important thing about the muon, which is also called the secondary cosmic ray, is well, this phenomenon is very well known. This phenomenon has been discovered more than 100 years ago. So, but one impressive characteristics of this spectrum of subatomic particles reaching the Earth, it's its energy. I'm showing this in this diagram. I hope you can appreciate the scales. On the y-axis is the flux, so the number of particles per square meters per second per unit of energy. And you can see that this spans over 30 orders of magnitude. The blue curve is actually measured data. But on the x-axis, you have the energy at which these subatomic particles reach us. And this is on a scale that is very hard to comprehend, even for people that work with particle physics and very large scales all the time. For reference, the highest energy ever achieved by a particle accelerator is of the order of 10 to the 12 electron volts. That's 1 TeV. That's the LHC at CERN. We have measured cosmic rays with energies in excess of more than 1,000 billion times higher than that. What does it really mean? A subatomic particle is something very small. We like to say they're point-like, but they do have a mass. For scale, an electron has a mass of about 10 to the minus 31 kilograms. It's a very small mass indeed. At this energy, a muon particle, a subatomic particle, has the same kinetic energy of a baseball, a fastball. Now, of course, you wouldn't expect to feel anything if you get hit by something which only weighs 10 to the minus 31 kilograms, but you would be very scared of a fastball. Now, cosmic rays they do not knock us down flat, fortunately, because being subatomic particles, they cannot deposit all of their kinetic energy while traversing our body. Yet, they traverse us every day. In fact, if you look at surface at the depth of 0 meters, on average, everywhere on Earth, there is 15 million of these particles per square meter per day. They traverse us while we sleep, while we work, while we play, everywhere on Earth. The higher you go, the more radiation you're gonna encounter. But of course, this is not dangerous radiation to the extent that damages. That's how life evolved on Earth in the presence of this radiation. Now, being very energetic, these subatomic particles can penetrate the subsurface, but now they start to becoming attenuated. And you can quickly see that at 200 meters, now you only have 15,000 particles per square meter per day. Their average energy is higher, and then there is still even higher energy still, like I showed you before. And in fact, if you look now on the right, this is a collection of world data, cosmic ray flux measured on the ground, up to a depth, equivalent depth of about 13 kilometers of water. We don't have underground laboratories that deep, but we can measure at slant direction at a large angle through basically a whole mountain range. So again, look at the scale of the intensity. We have collection data that has been collected throughout the decades. I think the deepest point cosmic rays were measured at 3,000 meters depth in a mine in South Africa. And the problem was the temperature that was breaking the equipment very, very quickly. And also note that we have a prediction of how this distribution looks like. It's a very simple decay mechanism. This primary cosmic ray generates a cascade of subatomic particles, but what we call muons at the surface of the Earth, the secondary cosmic rays, come from the decay of just two particles, the pion and the kaon. And if you look now at shallower depths, this is again a collection of the world data we have. So this is a very well-known fact. You can read on Wikipedia or the particle data booklet. All right, how could this be useful? Well, the concept is that we can use this free radiation source to make images of hidden objects. And this is not my idea for sure. It actually started in modern times in the late 60s with the Nobel Prize winner, Luis Alvarez, Lawrence Berkeley National Lab, who had the curious ideas to investigate what's inside the pyramids. Because at that time, there was a suspicion that there was some hidden chamber inside the Great Pyramids of Egypt, but nobody knew what it was because it's all covered in granite. So in 1970, Luis Alvarez's team, they brought a particle detector at the bottom of the pyramids and they measured an X-ray of the pyramid. Unfortunately, they did not discover any hidden chamber, but that's not a problem with the physicists. That's more of a problem with the pharaohs. Since then, radiography has found applications primarily in geophysics. And this is another very good example, a Japanese team that has taken the radiography of a volcano. You can see here in this panel, it's a color-coded density scale. You can see the outline of the mountain. And as you would expect, in the middle of the mountain, there is a region of lower density. There is a void, in other words. And this is the caldera of the volcano, after all. Actually, these days, many volcanoes around the world, primarily in Italy, Japan, and also in other countries, are actually monitored by cosmic rays.
Son monitoreados con rayos cósmicos para potencialmente predecir la próxima erupción. Muy bien, demos un paso atrás con respecto a qué podemos hacer con las fuentes nucleares. Porque cuando hablamos con respecto a las aplicaciones, la densidad nuclear tiene una aplicación muy amplia. Eso es un geodoctor, esos son los rayos X, pero también tienen distintas aplicaciones. Por ejemplo, en gas y petróleo utilizamos las mediciones de densidad nucleares para caracterizar formaciones y de hecho es la manera primaria en la cual podemos buscar.
Nuclear density is very simple. You have a nuclear source of a given intensity and you measure the intensity after it has traversed the object. Now, it's so beautiful. It so happens that the ratio between the two intensity only depends on a universal constant, which is the same for all materials on Earth, essentially, and the density of the material that it traversed. So if I know what incoming flux is, and I measure the flux under the object, which is what you do at the medical X-ray, I can determine the density of the object. Your X-ray image, your bones are bright white because they're higher density than the tissue around you. And it's a very robust measurement, meaning that it's an absolute measurement. It doesn't depend on temperature. It doesn't depend on chemistry. However, the problem is that you have to have a nuclear source. And nuclear sources are generally dangerous, and they also not very penetrating because they cannot be very high energy. Now you see the connection, hopefully, with what cosmic rays promises you. Cosmic rays are an alternative nuclear source. It is free, it is safe, and I hope I convinced you, it is very deep reading because it can even traverse kilometers of underground depth. All right. More in detail, if you look at the concept of muon radiography, imagine that I'm measuring the muon flux at the surface of the Earth, and I'm measuring it at the borehole detector somewhere underground. The ratio between the two intensities gives me the density along each one of these lines that I sketched over here. So we call this a directional probe because it carries directional information. Muons travel essentially along straight lines, as you would expect, of bulk density. And why is this important? Well, consider any material, any rock in general. What we call the bulk density of the rock is the combined effect of the grain density of the grains of the rocks, so the crystals, if you wish, corrected by the pore space, because rocks are not fully compacted. There is, in most cases, there is always some porosity. So when you're exploring for oil underground, measuring this porosity is extremely important because that is the volume of oil and gas that you will find in your reservoirs. More in general, if you have a generic medium, you know that you can actually have a fluid inside the pore space. And now I'm considering the case of water, maybe close to surface. And it is clear that by measuring the bulk density, since we know what the material we're working with, and we know what the density of the fluid, in the case is water, we can actually say something about the content of the fluid, which is now the pore space, which could be fully or partially filled with water. But most importantly, in any material, we can detect density changes over time by observing the bulk density through nuclear methods. And this hopefully has very practical applications. And that's what I will focus about. One other point is there is an important distinction. Just like in medicine, you have an X-ray, which is a radiography. In medicine, you also have CT scans, which are called a tomography. In this case, it's a three-dimensional reconstruction of density. How does that happen? Well, if you have this is an example from Los Alamos. If you place your cosmic ray detector, muon detector under a mountain, in this case was a tunnel in a mesa, at different locations, such that there is always some overlap. Now we can reconstruct density in the full 3D sense, and these are the beautiful results. This is from a friend of mine, actually a fellow Italian, and she did an amazing job. Now we can do a whole density profile of a mountain. All right. So a distinction in my career is that I actually, by chance, happened to be the first one to ever build a cosmic ray borehole detector, meaning a detector able to detect muons underground and they could fit into a borehole for an industrial application. It's important to note that when you're talking about an industrial application, it's not just a sensor. You have to build everything around it. In this case, also a pressure housing, a connection to the outside world, the onboard power, the telemetry, and the data connection. This was a very fun project. This was the team that delivered the CRY, the first borehole detector. And this is a picture of the tool when it was installed in Northern Canada for the field test. Now, it's not that I built the first borehole cosmic ray detector because I'm such a visionary. There was a reason for that. And the reason that, that I identified was a potential application of using this deep reading density technology to map something that happens in certain oil reservoirs. Certain oil reservoirs, heavy oil in particular, are too viscous to move on its own. So in order to be produced, you inject steam underground, and the steam heats the reservoir, and now the bitumen melts and it drips to a production well. This is certainly a very dirty way of producing oil, but it meets important requirements. First of all, always happens at shallow depths. So that is good because the muon flux will disappear at very great depths. Secondly, it generates a big density change because you have all of this steam pushing away the bitumen, and it is a big density change. It is easy to observe. It is a slow process because this happens over the course of many months, over years. And very importantly, it has a it's a very consequential economical value. You can imagine you pumping steam underground, you may be spending $50 to $100 million a year, and you don't know what's going to come on the other side because it's still 9 months away. And it will make everybody nervous. So the application here was to build a monitor that can be on the ground and map any substandard conditions. And this always happened. Look at the difference between the PowerPoint on the left. We have a beautiful steam chamber. It's nice and uniform. And then look at data that was taken, in this case, with seismic measurements in an actual field. You see anything but something uniform. This shows that the process is much more complex and is much more inefficient than you would like it to be. All right, but that was then. Before moving to the field, we had to do a validation test. So I just want to spend a little time to discuss what we did. You see here a picture of the basement of my laboratory at that time. There is a test well. So this is a fairly deep borehole going into the basement slab. And in front of it, we have cover with these metal plates. We have a very large tank. This can hold almost 100,000 gallons of water. It's a very big tank. And this sort of gives an idea of the geometry. The test well, the detector was installed was lower to the bottom of the well. We were about 20 meters away in concrete from this water tank. And what happens, this is some of the hardware that we used in order to insert the tool into the well. And you can see here the wire and cable connection coming out and a winch. And then we measure when the tank was empty and when the tank was full. And what you see is, if you look at just the intensity of the muon flux, which I told you is only attenuated by density, you see that it's the same in all the azimuthal direction, except in a certain direction, which is the direction of the tank. Here you see that the difference between the blue and the red, which is in agreement with simulation, is essentially the amount of water in the tank. And you can also see that there was when the tank is empty, there is a big density void. There is a hole. So the average density coming from that direction is going to be a lot less than the average density in other direction. And since it's less density, that means I measure more cosmic rays. When I fill the tank with water, nothing changes except in the direction of the tank. Now I've replaced air with water. It's still less density than concrete, so there is still a cosmic ray flux excess. Another way to look at this data is to do a 2D projection, and you can see that's the position of the tool, this is the position of the tank, and now I'm just showing you the subtracted event rate before and after, and you can see there is a clear signal only in the direction of the tank. Maybe we do even better if I do a 2D projection on the plane of the basement. The little star is the location of the borehole and the well, and you can see again, there is an anomaly, but this anomaly is only in the direction of the tank. And there were some artifacts in the reconstruction that we could not fix at that time. All right, so that's what I used to do in the past. Now, having learned, so now I'm gonna spend some time to show how this led to the formation of our company, Muon Vision. All right, a little introduction about ourselves. You heard about me. With me, there is also Ricardo and Francisco, who are two engineers in Chile, in Santiago. We just started a year ago. We did receive some funding, however, and we're building our technology and prototype for upcoming field tests in Chile. We think that muoradiography, I hope I convinced you, is a general purpose technology. We think there is many applications across the mining world. And we're going to talk about that next. All right, so first, before we dive there, why Chile? Well, you could see in the previous slide, we are targeting the heap leaching process, and Chile is the Saudi Arabia of copper and then some more. But it's also, of course, a country that is dedicated to green technologies and innovation funds. We are very grateful for Corfu support, and we hope to get more. But for us, cosmic ray people, there is another hidden advantage, is the fact that most of the mines are in the very high mountain. And in the high mountain, you get more cosmic rays because there is less attenuation through the atmosphere. In fact, the biggest scientific cosmic ray detector is in neighboring Argentina, high up there in the Puna. So this is actually a significant factor for us. All right, so let's talk about some of the applications that we see of muon radiography. So I hope I spent some time to convince you that it's an accurate measurement. It can measure over very long scales, long distances, and it can measure density and particular changes in density. So this is a simple case study that we recently presented. We took a generic tailing pond, and then we did a full model of the tailing pond in 3-dimensional model of nuclear transport. We placed our detector in the model at 3 locations under the tailing pond. You can see here a density profile of the tailing pond. And what I'm showing here at the bottom is for each one of these positions, the accuracy we will get in determining how much water is still left in the tailing pond. As you know, the tailing pond is made of solid materials at the bottom, all the way to water at the top, and everything in between. It's a continuous gradient of decreasing water saturation, right? So when you actually integrate over the full depth of tailing pond, it's a lot of water. But how do you know how much water you have, right? So how can you see inside? So we think our technology could help see inside the tailing pond. And what I'm showing over here is the accuracy, or the error bar, with which we can determine water content. So at the, on average, you will think you'll have 30–40% water in the tailing pond. It doesn't really look like that because you only see the surface water. And this is the measurement, the accuracy of our measurement. There is even another application in mining, which has to do with slope stability. The cause of many landslides is excessive water accumulation. If you pay attention to the diagram here over here at the bottom, I've dug a big hole. And now I have a big problem because the water table was originally close to the surface and now moved below the water table. And now the water still wants to come up. And how we will try to come up, we will find a way. It will find a way, maybe through a fault line. It will accumulate behind the wall and it will seep. And people are aware of this because it creates this. This is a case of a copper mine in Utah, one of the historic copper mines in the US. As you can see, this is a fairly big landslide. Now, mining operators knew this was about to come because they can measure the movement of the wall. So in other words, the landslide was already taking place because the earth was already moving. So in this case, they could evacuate everybody. They actually thought that the landslide was not going to be a major landslide. And boy, they were wrong. They lost a lot of equipment, years of production. And the reason is because if you just look at the movement of the earth, it's too late. You have to look at the cause. Why does the earth move? That is because water accumulated in the slopes. And we think that our technology could also help here because by putting ourselves in the pit, we can look at density, we can do a radiography of the walls, and in doing so, we can detect fluid accumulations that are hidden, are behind the pit walls. And in general, detecting water and mine dewatering, as you probably know, it's a big concern in underground mines with all sorts of horror story or drilling into a tunnel, a previous tunnel that was not part of the mine plan, which is full of water and it covers everything and so forth. Another interesting application area for us is leaching heaps, and this is, of course, a Chilean specialty. I assume you're familiar with leaching. The most striking thing about the leaching process in general is the huge scale. It's immense. These are the biggest structures ever built by man. If you look a little bit more carefully, like I showed you before in the case of heavy oil in Canada, one thing is reality. You would imagine you have uniform distribution of your acid all throughout the heap, and you have uniform production and everything is beautiful. But in reality, it doesn't happen that way. There are many reasons why fluid percolation through a heap can be very complicated. They have to do with mineralogy, with compaction, with the fact that you're dissolving a mineral which creates some kind of fines or dust which migrates and plugs the pore space and blocks fluid percolation. And this has two bad consequences. One is the fact that effectively some areas of your heap are not getting enough fluid, and so they will never produce copper. Another risk is that you may accumulate fluid in above an impermeable zone, and now you create the risk of having a landslide or a collapse. This could be highly consequential, or it could also just simply lead to a material that is too wet, and heavy equipment will sink into it. Why is this important? It's important because the leaching process comes after all of the energy expenditure that took place at the mine. You mined the material, you transported it, you crushed it, you stacked it, you irrigate. And then at the end of the day, in many cases, the recovery factor can be fairly poor, between 40 and 70%. So there is a lot of copper left. And given the scale of the problem, you don't really have an option to replay this because the mine schedule goes ahead and your material goes to the botadero. So if we could improve the metal recovery through heap leaching, we would automatically decrease the energy footprint that each ton of copper has. We did a little case study of what this looked like. Again, a simulation. This is a concept of what our measurement, our installation may look like. This is what we are presenting to mining companies in Chile. So our sensor can just be buried under a lift. So it doesn't require a well. And it's a nuclear imaging detector. It measures cosmic ray particles one by one. Now we can project them on the surface of the heap and build a map. And we can do this continuously. It doesn't require a lot of power. Cosmic rays are already there. What I'm showing here on the right is the potential accuracy of our measurement. Now, in a leaching heap, you don't want to fill the heap with water, like your sandcastle will just liquefy and disappear. You want to have a water content, a saturation content in the pore space between typically 10 and 20%. Different mines, different mineralogies will have different numbers. My point is that with this technology, we could potentially measure the amount of water that has entered the heap in a directional sense, pixel by pixels, with an error bar that in most cases is less than 1%. And this is what I'm showing here on the right, is a projection on top of the heap. You can see there is a fine segmentation of 2 by 2 meter pixels. Each one of them is an independent measurement. They're all taken from the same sensor, but in different directions. And for each one of them, for each one of these pixels, we have a pyramidal voxel going to the detector, and we have basically measured the average density inside this funny shaped volume. I would also like to highlight another effect, which we didn't talk. Cosmic ray muons are nice because they are for free, but certainly we cannot turn up and down the source. It's what it is. And the measurement is statistical, meaning that if you only measure the passage of 1 million particles, you have so much accuracy, and 10 million particles, that much more accuracy. So that also means that, like a very old camera, the longer the exposure time, the better accuracy and resolution that we get. And I'm trying to convey this on the right. This is a scenario, our expected accuracy after 10 days, 40 days, and 120 days. What you see is that the volume, the region, the core region where our accuracy is better than 1% keeps on growing and growing and growing. This is because we can put more and more detail into the picture because we have measured more and more particles and we have better accuracy. All right. So with that concept, hopefully, Muon Vision will build something that looks like a control system for leaching heaps, something that can see inside the leaching heap, something that can be scaled to map the full area of a leaching heap. And now an operator can say, oh, there's some substandard situation over here. Let me zoom. Let me see what happened in this set of pixels over the past few weeks. How has the fluid saturation changed? And why would you want to do that? Because to maximize production, to maximize uniform fluid distribution. And how will we do this? Essentially invisibly, with invisible sensors that are there, are taking data whether you want it or you don't want it. So we can use a Netflix model. And hopefully, with that, we're gonna become a company that has access to this data for our client and can build intelligent analytics to further optimize the lixiviation process. But this is not the whole story. I mean, you cannot just sell a technology because it's a cool technology or you think it's a cool technology. There has to be a motivation. And we hope to convince mining companies, we hope to demonstrate, obviously we have not, and that's our challenge, that through our measurement, through optimizing the fluid distribution, we can recover more copper. And that's ultimately what matters. That's the bottom line. Assuming it's a 10% production increase, this could potentially be worth to our customers $200 million per year from a given site. Of course, we would have no claim to that. Our fee would be a lot less. But nonetheless, this is a big economical driver. Associated with it are the environmental savings and so-called ESG benefits. Now, these are very important to us, but they are less important to the bottom line of to the shareholders of the mining company in some cases. In this case, we actually did an analysis. The environmental benefits is, if you have 10% more copper production for the same energy, you have 10% less embedded CO2. And we'll see next, that could be very big. We don't really save energy, but our service will be equivalent to acquiring energy from 22 wind turbines per year. For instance, the same amount of CO2 we remove per ton of copper is equivalent of having installed 22 wind turbines and saving a lot of water as well. But there is also another benefit, which is much more important to the mining company, is the fact that you have a safer operation. Reducing the risk of landslide is very significant. You cannot easily put a monetary value to that, but you do know that if it does happen, you might be shot for a year or maybe more, or you might have a tragedy at your hand. So technology is never really what sells the product. What sells the product is the customer need, what I call the customer pain points. And in this case, it's the fact that the recovery is not as good as it should be. There is no carbon tax, but if there were, it would be very expensive and you want to remove carbon from copper, and then finally the risk of losing your operation. All right, so I think I am done and I'm happy to answer your questions. So in summary, I talked to you about cosmic ray muons. I hope there is nothing to be afraid and you have something fun to tell your friends that they're also being traversed by cosmic ray muons, whether they know it or not. It's an alternative, free and safe nuclear source. It's deep reading and potentially, if you have enough measurement time, potentially very accurate. And with this, we can quantify density or water content in a time-lapse way. Density changes, which we would interpret as water changes. The application is preventing a landslide in soils, in slopes, and recover more metal or have less embedded CO2 in the final product. So thank you very much, and I'm looking forward to your question. And I will stop sharing, I guess.
Thank you very much, Tancredi, for your presentation. I think it was very interesting, and I learned a lot. So now we will start the round of questions. And as I told you all before, you can send us your questions in the Zoom chat in English or in Spanish. So as we wait, I would like to ask you something. Mm-hmm. What would be your advice to us students on how to apply science based on your experience and learnings?
Learn what industry or society needs. It's very important to learn your science, and you're gonna get better with time. Nobody is born, I mean, some people are born with incredible talent. Some people struggle, but they finally get it, they understand. Be passionate about what you do, but be passionate about other people's problems. I've learned a lot from scientific papers, but I've learned a lot by industry conferences because the world is full of smart people and they have real problems. And, you cannot just say, oh, my technology will fix it. It's all a question of how and why.
Thank you. I'm looking here if we have some questions. Okay, so what has been for you the most challenging issue to go from the theory and the science to the production of this technology?
Convincing industries and companies to change. That's the story of my tenure at Schlumberger. My colleagues, they all like my ideas, but Ultimately, the company customers and the company, they are too conservative. But there is a reason for that. These people are already making a ton of money and they don't need anybody to, make more. So that's why they're not inclined to change. I like to say that, that's why certain operating systems that you find in a personal computer never changed for 15 years. They had the monopoly. Why would they change? But in certain cases, things are different. And mining is a good example because as we're going towards a green economy, we understand that the problem with CO2 is everywhere. And alternative energies are cool, but alternative metals do not exist.
Thank you. So we have a question here. It says, as you said, Chile is a mining country, and today a lot of people don't trust the mining industry because of its negative impacts on the planet. So given what you've learned, what are your thoughts on these issues?
Okay, so I work a lot with oil companies, right? And I don't particularly love them. It's not a passion of mine. I like to say that generally we, so for instance, take a mining company. Mining companies, yeah, they have big operations and they make big money. But if you look at it the other way, they don't have big margins. It's nothing close to what Apple charges on your phone. And so they're actually struggling to provide something that ultimately, whether we like it or not, we all need it because we need electrical wires and we need thermal exchangers, and those are made of copper. Mining companies are very careful. My impression of it is that they are actually very careful on maintaining, of improving their status and maintaining sustainable production. They would love to do it, but they have to be reassured that they can do this without sacrificing their existing operation. It's too bad that many people do not trust the mining industry. I do not know the mining industry that well, but it's not made of evil people that are trying to conspire against us. It's made of people that have real problems, are passionate about their work, have many clever solutions, and they're trying to do the best that we can. I think that the focus should be more also on the consumers. Think about it next time you buy new clothes or take a new trip.
Thank you. So if anyone has another question. Okay, there's one. Claudio wants to know how important it is that the different industries focus on the sustainability issues.
To me, it's very important as a citizen, but it's not important for a corporation. Now, corporations don't exist just because they are there, right? They are made of people too, and people are part of a society. So the corporation has no incentive. That is also going to many cases, it has no real incentive to improve their product. But we as society have an incentive to make sure their product are clean or good or respect environmental regulations and so forth. So I like to say it's up to us. It's unlikely that free market forces themselves, they're just going to fix a solution on their own. In most of our recent history, it's always regulations that actually improve situations. So, and regulations is up to us as citizens. So let's not forget about that.
So thank you very much again, Tancredi. It has been a pleasure to share and learn from all your work.
You're welcome. Thank you.
Thank you. So now Matias Alcalde, representative of the Chilean California Council, one of
from the council,
partner organizations of the event, will say a few words to give closure to the event.
Many thanks, Bernardita. It's a pleasure to join you today and everyone who's been working so hard for this event. Pregunta, ¿es en español o en inglés?
English or Spanish? That's the question.
As you want, as you want.
Pero de preferencia es inglés.
But as a preference, English or Spanish? What do you prefer?
No, if you want to talk in Spanish, there's no problem.
Bueno, perfecto.
Okay, perfect. I just wanted to thank all of you, the students. We have been impressed with the work level you've put you have for this meeting, for this event, to regroup the 6 Sustainable Development Goals in a moment where we learn in different depths. And
importante que nunca ese tipo de aprendizaje. Creo que seguir estudiando para nosotros los jóvenes, yo también me siento uno de ustedes todavía, es súper importante. El futuro que se viene requiere de mucho conocimiento, requiere de mucho estudio. Por lo tanto, el llamado a seguir haciendo estas instancias donde nos encontramos de distintas formas, con las distintas innovaciones. Cada evento tiene sus propios estilos, que también es súper interesante en este mundo que nos virtualizamos. Pero lo importante es que estamos en etapas profundas, estamos en puntos de inflexión, donde los próximos 10 años son los que van a marcar gran parte del futuro de nuestros niños, del nuestro, de ustedes, de todos nosotros. Por lo tanto, creo que entender que cada uno es un verdadero factor de cambio es importante. El momento es ahora, no es mañana, es ahora, y la responsabilidad parte de nuestras actividades de todos los días, pero también donde nosotros ponderamos nuestros intereses. Creo que todos los ejes económicos, sociales, de las actividades tienen que tener una componente de impacto. Al igual como decía el anterior panelista, que me encantó las palabras que usó, el poder de los consumidores está ahí, el poder de las empresas mismas también está ahí para hacer el cambio, porque ya nos damos cuenta que no puede existir una economía que no contemple estos objetivos de desarrollo sostenible, simplemente no es viable. Las corporaciones, como decía recién, tienen su opción, no tienen el incentivo, pero próximamente van a estar obligados a tenerlo. Las corporaciones trabajan con riesgo y retorno, ¿cierto? Riesgo y retorno, y con eso miden sus éxitos. Pero la variable de impacto se va a empezar a medir. Ese es un estudio que está avanzando cada día más, sobre todo en Europa, en Estados Unidos. Por lo tanto, medir impacto se va a tornar cada vez más importante, y acuérdense que el día de mañana va a ser obligatorio. Por lo tanto, cualquier corporación, cualquier empresa, cualquier organización que no tenga esa variable incorporada a su diario que hacer, debería hacerlo lo antes posible, porque para allá va la cosa, y tenemos que medir esos temas, tenemos que generar los incentivos. Nosotros desde el Chile-California Council estamos justamente en esa senda, en tratar de acercar conocimiento. Como ustedes quizás han leído, Chile y California realmente son mellizos transhemisféricos, por muy cliché que suene, pero de verdad en el norte y en el sur compartimos una geografía similar que nos cubre en los dos extremos un cordón montañoso drenando sobre valles fértiles que desembocan en el Océano Pacífico, con más o menos 60 años de historia de diferencia en términos demográficos, de crecimiento poblacional. Por lo tanto, hay una cantidad de curvas de aprendizaje a favor de cómo el ser humano va creciendo frente a los mismos recursos naturales, que es fascinante, y por lo tanto se hace bastante importante entenderlo en las etapas que estamos, etapas profundas, que ustedes ya saben muy bien todo lo que nos ha tocado entre cosas pandémicas, sociales, económicas, de todo tipo. Por lo tanto, entender las curvas de aprendizaje a favor en eventos como lo que ustedes organizaron, para nosotros es realmente importante, un tremendo aporte, quiero que se sientan muy orgullosos. Además, yo les hablo con esta pasión porque soy de la Escuela de Ingeniería. Yo me gradué, me titulé el 2010 de ingeniero de recursos de civil hidráulico. Por lo tanto, nada, felicitarlos, llamar a que se queden en las mesas. Creo que también es importante lo que viene ahora ustedes, que organizaron unas mesas interactivas, donde ahí se convierte, donde ahí se profundiza más, donde ahí se relaciona más, y donde pasan cosas que uno no espera que pasen. Por lo tanto, ojalá que se queden todos a lo que está programado por la organización con respecto a las mesas. Y eso, cuenten con nosotros. Aquí hay un lenguaje que acercar, hay un lenguaje público, un lenguaje privado que tiene que empezar a trabajar juntos. Es un tema de optimización, de ver más lo que ocurre, de empatizar más con los distintos sectores. Bueno, y en esa lógica vamos a seguir navegando. Esperamos hacerlo junto a ustedes nuevamente y felicitarlos. Realmente el nivel de profesionalismo y dedicación que hicieron para este evento es ilusionante de ver que vienen tan activados a la salida de una escuela de ingeniería. Así que cuenten con nosotros, y nuevamente muy agradecidos. Gracias, Bernardita.
Muchas gracias, Matías, por tus palabras, y muchísimas gracias también a Chile California Council por acompañarnos y apoyarnos en todo esto, que ha resultado súper bien y estamos muy felices. So thank you very much all for your assistance, from the ISEL team. We hope you liked it and that you continue to enjoy and learn from our remaining exponents at the networking tables. Remember to check our website, isel.inc.uc.cl, and our Instagram, isel_KUC, to keep track of the information of the event. So that's all, and we hope to see you at the networking tables later. Thank you.
Chao, gracias, que les vaya bien.